Hello everyone, I'm Danica Gail Suaybaguio and I'll be discussing fundamental theorem of arithmetic. Before proceeding to our main topic, let's talk first what are prime numbers. Prime numbers are the natural numbers greater than 1 with exactly 2 factors. In example, 1 and the number itself. So basically, prime numbers are counting numbers or whole numbers greater than 1 that can only be divided by itself or by 1 to get a result of a whole number. So let's list some numbers greater than 1 and identify if it's a prime number or not. First, the number 2. We can only have 2 if we multiply 2 by 1 or 1 times 2. Remember, 2 times 1 and 1 times 2 is just similar. Its only difference is the order, but the order is irrelevant in factoring. Therefore, it is a prime number. Next is the number 3. Similar to 2, 3 can only be represented by multiplying itself to 1. So 3 is also a prime number. Next, we have 4. 4 can be represented by multiplying itself by 1. But it can also be represented by multiplying 2 by 2. Therefore, 4 is not a prime number, as it can be divided by a number aside from itself and 1. 5 is represented by 5 times 1. Therefore, it is a prime number. 6 is also not a prime number. There are countless of prime numbers existing, but let's stop with the number 6. Now we know that prime numbers have only 2 factors, the number itself and 1. So what are the numbers with more than 2 factors called? Composite numbers are numbers with more than 2 factors. We already listed numbers 2 to 6 earlier and tried to identify which of them are primes, and we found out that 4 and 6 are not. Therefore, using the definition of composite numbers, we conclude that they are composite numbers, or numbers with more than 2 factors. More examples are as follows. We have 8, 9, and 10. Let's finally proceed to our main topic. So what is the fundamental theorem of arithmetic? The fundamental theorem of arithmetic states that every positive integer except the number 1 can be represented in exactly one way apart from rearrangement as a product of one or more primes. This theorem is also called the unique factorization theorem. The fundamental theorem of arithmetic is a corollary of the first of Euclid's theorems. Anyway, that's too much words, too hard to process, right? So I also put here its simpler version. Suppose n is an integer larger than 1, then n is either a prime or a product of primes. It means that every integer or natural number that's greater than 1, that is 2 and above, is either a prime or a product of primes. The factorization of n into a product of primes is unique except for the order of the factors. This means that there is only one composition of prime numbers that made up a composite number. For example, the prime factorization of 4 is 2 times 2, or 2 squared. Therefore, 2 times 2, or 2 squared, cannot be the exact prime factorization of other numbers. Think of the number 4 as a lock, and 2 times 2 as a key. You can't open number 6 by the key used in opening number 4. Similarly, you can't also open lock number 4 using any other key or prime factorization. Let's prove it to see if this is really valid and true to all cases. But before that, we first need tools to help us prove the theorem. First, the well-ordering principle. Every non-empty set of non-negative integers has the smallest element. Second is generalization of Euclid's lemma. If P is a prime and P divides a sub 1, a sub 2, all the way up to a sub n, Then P divides A sub I for some I with I greater than or equal to 1 but lesser than or equal to n. Now we move on to proving the first statement. First statement states that n is either a prime or a product of primes. So here we are trying to prove that there exists a number that is neither a prime nor a product of primes. As you can see, we are making a contradiction of the first statement. First, we let S be the set of positive integers that can't be factored into a product of prime, include the case where there is only one factor. S must have a smallest element n. Where did we get this statement? So this is based on the well-ordering principle. We know that n is not a prime, therefore it must be a product of two numbers, except for 1 and the number itself. This means that a and b is greater than 1 but lesser than n or the number itself. Remember that n is the smallest positive integer that can't be factored into primes. And as we stated just a moment ago, a and b lies between the number n and 1. Therefore, a and b must be primes. However, n is equal to a times b, which are prime numbers. So n is, after all, a product of primes. And so it doesn't support our contradiction to the statement. This means that the first statement is true or a tautology. The second statement states that the factorization of n into a product of primes is unique except for the order of the factors. Let's try to prove it using its contradiction. Let S be the set of positive integers with non-unique prime factorization. We are trying to prove now that a number has more than one prime factorization. We know by well-ordering principle that n is the smallest element. So n is equal to p sub 1 all the way up to p sub r equals q sub 1 all the way up to q sub s, where p sub I and q sub j are all primes. As we can see, there are two different sets of variables, p and q, which is equal to each other. This is because we need to prove that there is more than one composition of prime numbers which product is equal to n. So we know that p sub 1 has to divide n. This also means that p sub 1 has to divide q sub 1 all the way up to q sub s, since it is equal to n. P sub 1 has to divide q sub j for some j. This statement is based on generalization of Euclid's lemma, meaning you should be able to divide p sub 1 to q sub j. It is stated above that p sub I and q sub j are all primes. Remember that 1 is not a prime number, so p sub 1 must be greater than 1, which leads us to the conclusion that p sub 1 and q sub j are equal, meaning to say they are representing the same number. So now we can cancel both sides, leaving us p sub 2 all the way up to p sub r equals q sub 2 all the way up to q sub s. P sub 2 all the way up to p sub r has to be lesser than n, because p sub 1 has been cancelled now. But n is the smallest integer with a non-unique factorization. That means that r is equal to s, since p sub 2 all the way up to p sub r is lesser than n. And there is no integer that is lesser than n that has unique factorization. Therefore, p sub 2 all the way up to p sub r is the same as q sub 1 all the way up to q sub s, except probably for the order. This debunks our contradiction to the second statement, and thus second statement is also true to all cases. I have prepared here an example to visualize it better. Let us try to find the prime factorization of 845. To better understand and visualize it, we'll be using a factor tree. Let's start first with the given, so 845. 169 and 5 is a factor of 845. So we have to put it right under 845. Since 5 is a prime number, we only have to work on 169. 13 and 13, or 13 squared, is a factor of 169. So we have to put it under 169. We completed factoring 845. As you can see, 13 and 5 are all prime numbers, and so the theorem has been proven. There is also another way of arriving on 13 squared and 5, but as stated, the prime factors didn't change, only its order. Therefore, the prime factorization of 845 is 5 times 13 times 13, or simply 13 squared times 5. So that would be all for today's lesson. I hope you learned something. Goodbye and God bless.